everyone, I hope you're doing well. Welcome to our next video. The section we're going to be going over is 3.3. I believe I'm just going to loop 3.3 and 3.4 into the same video. They flow really nicely together, so we'll see. I'll just see how long it's kind of taking and see if it'll be better to break it up or just do it in one. I'm thinking just in one. So 3.3 is sum and difference identities for cosine. Now there is a proof of these identities if you would like to take a look at it, but I'm not going to show it in this video. So cosine alpha plus beta is equal to, and so you may think that it's as simple as just taking cosine of alpha and then cosine of beta and then just adding them together, but it's a bit more complicated than that. Here's what the identity looks like. Cosine alpha times cosine beta minus sine alpha times sine beta. Also, we have another version of this identity where if you subtract two angles and take cosine of them, it would be cosine alpha times cosine beta plus sine alpha times sine beta. Now, right now, I mean, these are just identities that I've introduced to you, so you may wonder, what are we even about to use this for? Like, what is the purpose of this, you know? So here's an example of why we would use this. Starting off with cosine, let me write some directions in here, sorry. Let's say find the exact value for cosine 75 degrees. Now, when you're asked to find the exact value, what we're looking for is like, what is cosine of 75 degrees? So for instance, we know what cosine of 30, what cosine of 45, we know cosine of 60. And so we're being asked, what is cosine 75 degrees? The issue here is that cosine 75 degrees does not have a reference angle that we are familiar with. So remember that we have our table, so we have sine, cosine, 30, 45, and 60. And so sine is 1/2, root 2 over 2, root 3 over 2, cosine root 3 over 2, root 2 over 2, and 1 over 2. So all the angles that we've looked at previously when doing exact value have had a reference of either 30, 45, or 60, meaning they've been either 30, 45, or 60 degrees from the x-axis. If we look at 75 degrees, it is 75 degrees from the x-axis, so we can't use our table to help us. That's why we can use these identities. So if we think of two angles that could add up to 75 degrees, potentially being 30, 45, or 60, some combination of those, we can use the identity. So 75 degrees is equal to 30 degrees plus 45 degrees. So I'm going to use this identity right here. So instead of saying cosine of 75 degrees, I can say, well, that's equal to cosine of 30 degrees plus 45 degrees. And so now I'm treating this like my alpha, this like my beta. and I'm going to write in the rest of the identity. So I'm going from this side to this side. So this is going to be cosine 30 degrees times cosine 45 degrees minus sine of 30 degrees times sine of 45 degrees. Sorry, I ran out of space there. And so then the nice thing about using this is that we already know cosine of 30, cosine of 45, sine of 30, and sine of 45 because those are in the table. So cosine of 30 is square root 3 over 2. Cosine of 45 is root 2 over 2. Sine of 30, 1 over 2. Sine of 45, root 2 over 2. Then it's just a matter of simplifying. So I get square root of 6 over 4 minus root 2 over 4, which can simplify to root 6 minus root 2 all over 4. We can do another one of these. So let's say find exact value for cosine. Let's do one in radians. So this one's going to be pi over 12. So pi over 12 is not something I know like any kind of reference or anything like that about. So I can either try to add angles or subtract angles to be able to get pi over 12. So let's take a look at the angles we do know about. So I know that I have pi over 6, which is 30 degrees, pi over 4, which is 45, and then pi over 3, which is 60. So if I try to combine these in some way to get to pi over 12, one, let me make all of these have a denominator of 12 because then maybe it'll be easier to work with. So this would be 2 pi over 12. Pi over 4 would be 3 pi over 12. And then pi over 3 would be 4 pi over 12. So I want to either add or subtract these in some way so that I can get to pi over 12. And I only need 2. I don't need to use all 3. So we have 2 options here. I can either say pi over 12 is equal to 3 pi over 12 minus 2 pi over 12, or I can use 4 pi over 12 minus 3 pi over 12. Either one will give me pi over 12, so either one would be a good combination to use. So I'm starting with cosine pi over 12, and I'm saying that that's equal to cosine, and I'm just going to pick 4 pi over 12 minus 3 pi over 12. Now just to make this easier on myself, I'm going to reduce those back to what they originally were. So 4 pi over 12 is really pi over 3, and then 3 pi over 12 is really pi over 4. I really only wrote them with the denominator of 12 so that I could see what to add and subtract. And now I'm going to use the identity. So a reminder, the identity is written up here. And since this one has a subtraction, I'm using this identity right here. So I have this side already written. So my pi over 3 is like alpha. My pi over 4 is like beta. So I'm going to fill in the rest of the identity. So this gives me cosine pi over 3 times cosine pi over 4 plus sine pi over 3 times sine pi over 4. Cosine of pi over 3, so that's the same as cosine of 60 degrees. It's going to be 1 over 2. Cosine pi over 4 is root 2 over 2. Sine of pi over 3, or sine of 60 degrees, is root 3 over 2. And sine of pi over 4 is root 2 over 2. This simplifies to root 2 over 4 plus root 6 over 4, which I can write as root 2 plus root 6 over 4. It cannot simplify any further than that. Now, just a little bit of insight here. If using the radians is causing too much of an issue for you, you can always just change to degrees. So pi over 12 times pi over 180, we'll turn it into degrees. Sorry, pi has to go at the bottom, so 180 over pi. You want the pi's to cancel, so 180 divided by 12, this would be 15 degrees. And so then pretty much what we looked at is we said pi over 3 is 60, pi over 4 is 45. So we basically did 60 degrees minus 45 degrees to get 15 degrees. So if seeing it in the degrees makes more sense, you could always switch it out in the beginning. Now sometimes we may need to use angles outside of the 30, 45, or 60, but we may need an angle that uses 35, 45, 30, 45, or 60 as like its reference. So let's look at this one. This one says find exact value of cosine 255 degrees. So what we want to do is we want to find two angles that basically lie on our unit circle that we already know, meaning it already has a reference of 30, 45, and 60 to try to get to 255. Now we can either add or subtract to get to 255. I get this question a lot, is how do you know whether to use the addition identity or the subtraction identity? Really, you could use either one. So sometimes. With the first one we did, it was 75, and it was just kind of obvious that 30 and 45 would add together to get 75. But we could have done some kind of subtraction as well. Example 2, this one you can't really add to get to such a small angle, so that's why we decided to subtract instead. Really, I would say that if your angle is smaller than 30, 45, or 60, or pi over 6, pi over 4, pi over 3, if it's smaller than one of those, you're probably going to try to subtract to get to it. If it's bigger, you'll probably just try to add. So you'll probably be adding more than subtracting for these types of problems. So what I'm trying to find is two angles that add up to 255. So I'm going to write one of the most common ones that I always get, which is 180 plus 75. People will say, okay, well, let's just do 180 and 75. The reason that you can't do this one is because of this 75. It doesn't have a reference of 30, 45, or 60. So it's not a good option. We can try something else. So think of maybe two different angles that I could use. I could do 210 and 45 degrees. The reason this one works is because 210 has a reference of 30 degrees, meaning how far is it from the x-axis? So 180 to 210 is 30 degrees, so it has a reference of 30. And then 45 has a reference of 45 because it's just 45 degrees. So this one would be good. That's a good option. We could also try 225 plus 30 degrees. This one works because 225 has a reference of 45, so that one works. Let's see. 195 plus 60. This one does not work because 195 does not have a reference of 30, 45, or 60. So I would say that would be a bad option. So we found two good options, so let's just go ahead and pick one of those. So I'm saying cosine of 255 can be written as cosine. And let's do 210 plus 45. 210 plus 45. So remember, this is acting like my alpha, this is my beta. I'm going to write the other half of that identity. So it'd be cosine 210 times cosine 45 minus sine of 210 times sine of 45. Cosine of 210 has a reference of 30, so I'll remind you of why that is. 210 is in the third quadrant. It is 30 degrees from 180, so that's why it has a reference of 30. So remember, cosine of 210 will have the same value as cosine of 30. Cosine of 30 is square root 3 over 2. But we have to be careful. It's in quadrant 3, so it'll have to be negative. Cosine 45 is root 2 over 2. Sine of 210, so that's the same as sine of 30 degrees, which would be a half. But be careful because it's negative since it's in quadrant 3. Sine of 45 would be root 2 over 2. Simplifying this, I get negative square root of 6 over 4 plus square root 2 over 4, which simplifies to negative square root of 6 plus square root of 2 all over 4. And it may be tempting, since you have a calculator, to find out what these answers are in decimals. But test 2 is going to say, just like test 1 did, do not leave your answer in decimals, exact answers only. Exact answers mean I want to see it with the square roots. I want to see it as a fraction. So that's actually it for 3.3. So I am going to go ahead and do 3.4 as well. 3.4 is sum and difference identities for sine and tangent. So just more of those identities, but now we're doing them with different trig functions. Something else I'd like to bring up is that those cosine identities that I wrote for you in the beginning, those will be given to you on a formula sheet for test 2. So you do not need to remember those. Same thing with the ones I'm about to write for you. So the identities for sine are sine alpha plus beta is equal to sine alpha times cosine beta plus cosine alpha times sine beta. If we want to subtract two angles, all it does is change that middle sign into a subtraction. So those are the identities for the sum and difference identities for sine. I'll give you the tangent ones a little bit later. And so these problems are going to be super similar to the last section. It's just now we're using sine, so it's going to be a slightly different identity. So I'll say find exact value, sine, and this one is 195. So again, with this one, we want to find two angles that could add up to get to 195. So let's see, we can do, a common one I'll get is 180 and 15. The reason that's no good is because I don't know anything about 15 degrees. Like I don't know sine, cosine, or anything of 15. So no good. We can do 45 and 150. This is good because 45 I know stuff about, and then 150 has a reference of 30 degrees. I can also do 135 plus 60. This one works because 135 has a reference of 45. So again, you have some options here. So let's see, I get sine of 195. Usually for me to find the two angles, I'll just take my angle. So I'll just take 195 and I'll subtract 30, 45, or 60 from it to just see if anything will work. So for instance, if I did 195 minus 45, I got 150. So 45 and 150. 195 minus 60, I got 135, and I could use both of those. If I do 195 minus 30, I get 30 and 165, and 165 does not have a reference angle, so I wouldn't use that one. So I'm just going to pick, let's do 135 and 60. So I'm saying sine of 195 is equal to sine of 135 plus 60, making sure I keep that in parentheses together. Then I'm going to write it out with the other half of the identity. So I get sine 135 times cosine of 60 plus cosine 135 times sine of 60. So this is like my alpha, my beta. Simplifying here, sine of 135 is root 2 over 2, but it's in quadrant 2, so that's going to make it positive. Cosine of 60 degrees is 1/2. Cosine of 135 would be root 2 over 2, the same as cosine of 45. However, it's in quadrant 2, which makes it negative. And sine of 60 degrees would be square root 3 over 2. If you are having trouble getting any of these fractions that I'm writing down, I would recommend taking a look at 1.4 and also maybe 1.5 or 1.6. That's where we did problems like this. This becomes square root 2 over 4 minus square root 6 over 4. The only thing we can do is write that as one fraction. Square root of 2 minus square root of 6 over 4. It cannot reduce any further. Something else pretty common that we can see is sometimes maybe you'll go the opposite way with the identity. So let's see, find exact value. This one's actually going to use the cosine identity. So let's say cosine of 193 times cosine 32 minus sine of 32 times sine of 193. So it's looking like maybe my 193 is like alpha, my 32 is like beta. And so it's looking a lot like the cosine sum identity. Because if you go back and look at the cosine sum identity, here's what that looks like. It said cosine alpha plus beta is equal to cosine of alpha times cosine of beta minus sine alpha sine beta. So we're seeing the same thing, it's just that these two were switched. However, that really shouldn't cause a concern because multiplication is commutative, so it doesn't matter which one comes first when it's multiplication. So what we can do is we're seeing this side of the identity, so we can go to the smaller side. Say this is equal to cosine 193 plus 32. Which would be 193 plus 32 is 225. Well, 225 has a reference of 45 degrees, and it's in quadrant 3. So this will equal negative root 2 over 2. Because cosine of 45 is root 2 over 2, and then it's negative because quadrant 3. So sometimes you could see a problem like this where maybe you go from the longer side of the identity into the smaller side. Here's another one, another maybe type that you could see. This one just says simplify. And it says sine negative t times cosine of 2t minus cosine negative t times sine negative 2t. So this one is just asking us to simplify using the identity. So first I want to remind you about even and odd identities. So sine is an odd function, which means if you have a negative in the parentheses, that negative can move out to the front. Cosine is an even function, meaning the negative can just go away. So if I use those identities, so first I'm using even and odd identities. I'm going to pull this negative out to the front. This is getting left alone. So I didn't do anything with that. Minus cosine, the negative can just go away, so I just got rid of it. And then again with this sine over here, the negative can pull out to the front, so it'll be negative sine 2t. Then I'll just simplify, so I get negative sine t times cosine 2t. Negative times negative is a positive. Cosine t sine 2t. So these negatives here just canceled out. Now just to make it look a little nicer, I'm going to write it as cosine t sine 2t minus sine t cosine 2t. So I swapped it around a little bit. That way I could see the minus in the middle, just like it does in the identities. So then I would go to what you guys will have as an identity sheet, and I'll try to figure out if this looks more like a cosine or a a cosine or a sine identity, and then I'll decide is it sum or is it difference. I'd say this looks very similar to the sine identity that says sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta. Say it looks very similar to that. It's looking like alpha is 2t and beta is just t. So I can write it as the other side of the identity and just say sine 2t minus t, which simplifies to sine t. And that's what we wanted for this one. So we just simplified this one, but we had to use the identity to do it. Next is another type of problem that we could see using the identities. So example 4, I'll say find the exact value of sine alpha plus beta if sine alpha is equal to negative 3 over 5 and cosine beta is equal to negative 1 over 3 with alpha in quadrant 4 and beta in quadrant 3. Something to know here is that we do not actually know what alpha and beta are. We know where they are, but we don't know what they are. Like, I don't actually know what angles they are. So when it says to find the exact value of sine alpha plus beta, I'm going to first use the identity. So sine alpha plus beta is equal to sine alpha times cosine beta plus cosine alpha times sine beta. And again, those identities will be given to you on an identity sheet for test 2. Now, while I use this identity, I already know what sine alpha is. They gave me that. I also happen to know what cosine beta is because they gave me that. The issues are that I don't know what cosine alpha is, so I don't know this one, and then I also don't know sine beta because they didn't give them to me. However, I can go find them. So if they gave us sine of alpha is equal to, here, let me write it here. Sine of alpha is equal to negative 3 over 5. Remember what sine is in relation to a triangle. So they said that alpha is in quadrant 4, so I'm going to draw alpha in quadrant 4. And let's make a triangle. Sine is opposite over hypotenuse. So this will be negative 3, this will be a 5. Now I got to think, okay, well, how can I find, like, I want cosine of alpha. If I want cosine of alpha, then I want the adjacent over the hypotenuse. So I'm looking for adjacent over hypotenuse. So we need to find out our adjacent side. So to do that, I can take and do Pythagorean theorem. So I can do, I'm looking for, let's call it b. Do a negative 3 squared plus b squared is equal to 5 squared. Simplifying, I get 9 plus b squared equals 25. B squared equals 25 minus 9, which will be 16. So then b must be equal to 4 if I take the square root. Now be careful here that b should be a positive 4 only because it's on the positive side of the x-axis. So now I know that cosine of alpha is equal to 4 over 5. So now I'll be able to plug it in whenever I need it. Next, I'm going to do the same thing, but I'm going to do it with beta. So beta, they said, was in quadrant 3. I'm going to make a triangle. Remember, your angle should always touch the x-axis. So when it said that cosine beta is negative 1 over 3, that was giving me the adjacent over the hypotenuse. So this would be negative 1, this would be 3. I should expect my y value to also be negative. So I'm going to use Pythagorean theorem to get the other side. Let's just call it A, I don't know. Or we can call it B again, whatever you want. I'm picking A, but that's just because. B would probably be nicer since it's across from beta, so it'd probably be nicer if we used B, but it really don't get too caught up in it. It's just Pythagorean theorem. So negative 1 squared plus A squared is equal to 3 squared. So I get 1 plus A squared equals 9. A squared is equal to 9 minus 1, which is 8. Take square root of both sides, so I get A is equal to square root of 8. Remember we said it should be negative because It's in quadrant 3, so the y should be negative there. You do want to be a little careful here because my math lab is going to make you reduce this radical. And so this radical reduces into negative 2 root 2. So again, remember what we're looking for. We're looking for sine of beta. So sine of beta would be equal to the opposite over the hypotenuse. I just found that my opposite side is negative 2 root 2 over the hypotenuse, which was 3. Now I have all the information I need to come back to this identity. So sine of alpha plus beta is equal to sine of alpha they gave me. It was negative 3 over 5. Cosine of beta they gave me. It was negative 1 over 3. I'm going to keep parentheses here because of the negative, because it's multiplication as well. Then I have plus cosine alpha I found. It was 4 over 5. And sine of beta I found was negative 2 root 2 over 3. Now it's just simplifying, so this would be positive 3 over 15 plus, minus, 8 root 2 over 15. And the top can't actually combine, but we can write it as one fraction. So 3 minus 8 root 2 over 15. Is that fully simplified? Some common mistakes that I'll get for this one is people like plugging in, like instead of replacing the whole thing of sine alpha with negative 3 over 5, they just plug that in as the angle. I talked about that before test 1, and it did happen on test 1 as well. It does pretty much every quarter. And usually it happens on test 2 as well, even though I do mention it. So please do not ever plug in one of these ratios as just the angle. It's not the angle. It's the entire thing. It's sine at that angle. We don't know the angle, so you can't plug anything in for just the angle. So just be careful there. Some more identities that will come up on your homework is the cofunction identities. I do not test on these, but it's something that will come up, and I think it's good practice. It's not very difficult to work with, but something to be aware of. Cosine of an angle is equal to sine 90 degrees minus that angle. Sine of an angle is equal to cosine 90 degrees minus that angle. And I'll give you an example, of course, of when this might be used. Okay, so let's do this next example. This one, what number are we on? 5. It says find exact value. And this one is sine 193 times cosine 32 degrees plus cosine 32 degrees times cosine 58 degrees. Did I write this correctly? Give me just a second. I want to make sure I write it the right way because sometimes, these can be kind of weird. So I think I need to change one of these. Hold on, give me just a second. Sine 193 cosine 32, and then we'll write it as cosine 193, and then cosine 58. Yes, this is what I want. Sorry, these are always kind of weird, so I gotta make sure that I write it down correctly, especially when it's ones that I've made up. All right, so let's work on this one. So I would say that this one, the issues that you kind of see with it is the fact that this part looks kind of like the sine addition identity, but then this part looks like the cosine. Also, we're seeing these angles match up, so that's nice because they're both alpha, like if we're kind of comparing it to our identities. So here's what I'm thinking. I'm thinking this looks a lot like this identity. I'll write it for us. Remember, you'll be given these on an identity sheet. So it's looking really similar to this identity. But right here is the problem. That right there is an issue. So what we can do instead is we can rewrite this identity. And we can say instead of writing cosine of 58, let's do sine 90 minus 58. 90 minus 58 is 32. So if I rewrite this, I get sine 193 times cosine 32 plus cosine of 193 times sine of 32. And that looks a lot more like the identity that I was expecting to see. So my point is that sometimes, like, if you're seeing an identity and if it looks like it's just like a cosine or a sine that's messed up and maybe one of the angles or something like that, you might need to use one of the co-function identities. Now again, I do not test on this, but it does come up in the homework. So if I simplify this, I'm going from the long side of the identity to the shorter side. So this would become sine 193 plus 32. So let's see what that gives me. 225. And sine of 225, so 225 actually has a reference of 45 degrees, but it's in quadrant 3. So sine of 45 is root 2 over 2. And then since we're in quadrant 3, it needs to become negative. So here's that answer. So that's all for we did cosine, we did sine. Now we're going to look at some tangent. So let me put a note here. We're looking at tangent now. I'm going to show you the tangent sum and difference identities first. Again, these are given to you on a formula sheet, which I can show you. So tangent of alpha plus beta is equal to tangent alpha plus tangent beta divided by 1 minus tangent alpha times tangent beta. And then the subtraction version of it is tangent alpha minus tangent beta divided by 1 plus tangent alpha tangent beta. And so we're going to use it for the same like reasoning. It's just that we'll have just tangent instead of sine and cosine. So let's look at an example. This one I'm actually going to give us a negative angle just to work with. This is example 1 of tangent, but I really should say it's example 6 of this section. So again, I'll just say find exact value. And I'm thinking of maybe doing 2 of these. So I'll do part A and part B. So let's see, for part A, let's look at tangent negative 15 degrees. There's 2 ways to deal with a negative angle. One, you can use the fact that it's even or odd. So if it's cosine, it's even. If it's tangent or sine, it's odd. And so an odd function, the negative can be moved out to the front, and then you can just kind of carry it in the front with you the entire time. So that's one option. Your other option is just to work with the negative angle. I guess technically there's a third option. Your third option is to use coterminal angles and add 360 to this to make it no longer a negative angle. So negative angles, you have a few options. One, you can use the even or odd identity. 2, you can just work with the negative. Or 3, you can use coterminal, which means add 360. So 3 different ways to attack this problem. I find most people just work with the negative, so I'll just show you that way first. So for tangent negative 15 degrees, we want to think about 2 angles that we could add or subtract to get to negative 15. So of course, I do recommend you pausing and maybe trying this one out on your own. It's pretty similar to other ones. The simplifying is a little hard on it though. So what we could do is we could do 30 minus 45. That would get me to negative 15. It being such a small angle, 15 is kind of what tells me I probably need to subtract. And then because it's negative, I'm just going to do the bigger one minus, I'm sorry, the smaller one minus the bigger one. So it's looking like this is my alpha, this is my beta. So I'm going to plug it into the other side of the identity. So I get tangent 30 minus tangent 45 divided by 1 plus tangent 30 times tangent 45. Tangent of 30 degrees, I'm going to go ahead and write my table. So I've got sine, cosine. So 30, 45, 60. Sine is 1 over 2, root 2 over 2, root 3 over 2. Cosine is the opposite. And then because I want tangent, I'm going to go ahead and add that in. So tangent is sine over cosine. So for 30, it'd be 1 over root 3. For 45, it'd be 1. For 60, it'd be root 3. So for 30 degrees, it's 1 over root 3. Tangent of 45 is 1. Tangent of 30 is 1 over root 3. And then tangent of 45 is 1. So here I get 1 over root 3 minus 1 over 1 plus 1 over root 3. I cannot tell you how many times I have seen people write that their answer to this is negative 1. And it's because they're just canceling out the top and bottom. However, that can't happen when you have pluses or minuses in between. You can only cancel out top to bottom if it's like just multiplication. So the simplifying for this is a little difficult. It's because you don't want radicals in the denominator. And then also you have separate fractions, so you need to combine them into one fraction. So a couple things that we're going to have to do here to simplify this. First thing that we can do is let's multiply everything in here by the by the least common denominator. Least common denominator. So what we're going to do here is we're going to multiply by root 3 basically to everything, but what's really happening is this is what we're multiplying by. I want to be really clear about this. This is algebra. This is just algebra. But if it's a bit unfamiliar to you, I do want to explain like what's going on here. So I wrote the 1 over 1s. That way we can see everything as a fraction. And so when we multiply by root 3 over 1 over root 3 over 1, we're really just multiplying by 1 because we're multiplying the same thing at the top and the bottom. And top and bottom, if they're the same, it cancels out to 1. This is not the same thing as multiplying by both sides. There is no both sides to this because this is not an equation, right? We're just simplifying. So when I do this, I'll get root 3 over 3 minus root 3 over 1 divided by root 3 over 1 plus root 3 over root 3. So the whole goal of this was now we have some cancellations happening. So this becomes 1 minus root 3 over root 3 plus 1. Now we're not finished because we still need to get the radical out of the denominator. To do that, you have to multiply by the conjugate. I reviewed the conjugate in 3.2, so this would be root 3 minus 1 would be the conjugate. So this becomes 1 minus root 3 times root 3 minus 1 divided by root 3 plus 1 times root 3 minus 1. This becomes root 3 plus, let me write this correctly. So 1 times root 3 and then 1 times negative 1, so minus 1. And then minus root 3 times root 3 would be 3. And then plus root 3 at the end. Divided by, this would be 3 minus root 3 plus root 3, so those cancel. And then minus 1. So this becomes 2 root 3 minus 4 over 2, which can all simplify to root 3 minus 2. Wow, that was a lot. Now you can actually check your answer in the calculator because I can type into my calculator root 3 minus 2 and that gives me negative 0.26. If I type in tangent negative 15, that gives me negative 0.26. So I know that it's correct. But I don't want the decimal answer on your test. Please do not give me that on your test. So this is what my math lab is going to ask you to do. It's going to ask you to simplify all the way down. Even if you're, for people who are taking this later, if we're already on Alex by that point, they also want fully reduced answers. Okay, let me give you some hope for that simplifying. If you toned out, please tune back in. In the next section, I'll teach you another identity that you can use for tangent, and it requires way less simplifying. Like, seriously, so much less, it's crazy. So when I do tangent for like an exact value, I never use the sum and difference identities because they're just terrible to simplify. What I use is what we'll do in our next section, 3.5. So there is some hope for those of you who are like, oh my gosh, how am I going to know how to do that on the test? It's okay. It's easier with a different identity, and I'll teach you that one, and I think it'll go a lot better. I do have people use this identity on the test, and they just don't fully simplify. It's a minor deduction. It's not going to tank you on the test. So I did just want to do one more of these. I think I want to do, let's do, sorry, I'm thinking of one. I gotta come up with a good one. Yeah, I like that one. All right, let's do part B, tangent, and let's do another negative, just because so that you can get some experience in it. 285. So much bigger. And this one I'm going to show you another way to deal with the negative. This one I'm just going to move the negative out to the front. Cosine is really nice if you have the negative because then it just goes away because cosine's even. For sine, you would also just move it out to the front. So 285. So let's see, for 285, I want you to pause and please think of two angles that could add up to 285. I'm going to use 60 and 225 for this one. So then I'm going to write in with my identity, and I just have this negative like hanging out the whole time. So I'm going to put parentheses around my actual identity part. So it would be tangent 60. Remember, I'm using these identities up here. This one's the addition one, so it'll be this one. Plus tangent 225 divided by 1 minus tangent 60 times tangent 225. Let me make sure I wrote that in correctly with the identity. Yes, okay. Next, I'm simplifying. So tangent of 60, if we go back up to my table, tangent of 60 was root 3. So this becomes root 3. Now 225 has a reference of 45, and it's in quadrant 3. Quadrant 3, tangent is positive. So that's going to be 1. If it was negative, you would want to put that in here. And then I have 1 minus tangent of 60 is square root of 3 times tangent 225, which is 1. This one's a bit simpler to simplify. So square root of 3 plus 1 over 1 minus square root of 3. So again, either you can have the negative out in the front up until the very end and just distribute it in, or maybe we can do it now if you'd like. So if I do it now, I can either do it to the top or the bottom. You can choose. I'm just going to do it to the top. Negative square root 3 minus 1 over 1 minus root 3. I still need to multiply by the conjugate, which in this case would be 1 plus root 3. I'm going to go ahead and multiply this out and FOIL it out just like I did for the last example. So this would be negative square root 3 minus 3 minus 1 minus root 3 divided by 1 plus root 3 minus root 3 minus 3. So this becomes negative root 3, negative 2 root 3 minus 4 divided by negative 2, which becomes root 3 plus 2. Yep, and that's it. So again, in 3.5, we're going to use another identity to deal with tangent, and it is way easier to simplify. So I know that one was kind of a longer video, maybe, but maybe, I don't know. I don't really remember when I started it, but it was 2 sections. So I hope y'all have a wonderful day, and I hope this isn't too intense. I know it is a bit difficult though, so if you are having any trouble or any issues, please reach out to me and I would love to help you. But again, I hope y'all have a good day, and I'll see you in our next video.